Hi everyone. So today let's learn about an essential concept in Olympiad geometry. So alternate segment theorem talks about a circle and a tangent at a point P on the circle. And suppose you have a chord whose one of the endpoints is the point P and other one is some random point on the circumference. So it deals with the angle made by this chord with the tangent and the angle subtended by this chord on its alternate segment. Both turns out to be equal. So we will solve one problem related to this, which makes your understanding more rigid. But there are a lot more difficult problems out there which you must try. So this is particularly useful for contests like IOQM and RMO as well as AMC. So I hope you will enjoy it. Let's get started. The alternate segment theorem is an important property or theorem related to circles and tangents. There are various names of this like tangent chord theorem and so on. And let's see what it describes. Consider a circle and let's take a point and a tangent at that point. Let's call that point to be P and the circle to be gamma. Consider a chord whose one of the endpoints is P. Maybe the other endpoint be Q. So it talks about some angles, but before that, let's define some parts of the circumference of the circle, which is divided by this line PQ. So there are two arcs. One is the arc that is contained in the acute angle made by the chord and the tangent. So this is the segment or arc. Notice here that arc and segment represent the same entity. So here it is a segment in the angle. The reason is because this segment of the circle is sort of piercing the angle. So it is going through the angle, right? So that's why we call that segment to be the segment in the angle. So we consider acute angle at first. So this is the meaning of segment in the angle, and the other segment, which is denoted by this arc on the circumference, which is not actually piercing the angle, is named to be the alternate segment of the, let's call the angle made by the chord with the tangent to be theta. So for now we can consider the acute angle. Then the angle subtended by the chord PQ on the alternate segment is also theta. That means that when you connect one end of the chord to the point on the alternate segment, you can take any point on the alternate segment, say x and p to x, then the angle made by QXP will also be theta. So that's how the statement goes. So writing this in words, we get angle made by the chord with the tangent at one of its endpoints equals the angle subtended by the chord on the alternate segment, where the alternate segment is considered as the segment not intersecting the angle on the alternate segment. So the proof of this will be quite elegant, because suppose if we consider the center of circle as O, then drop a perpendicular from O to the tangent, which will be the point of tangency P. And we know that it makes 90 degrees. So hence the angle OPQ would be 90 minus theta. And notice that OP and OQ are radii of the circle, and thus OPQ is an isosceles triangle, and we get OQP equal 90 minus theta. And therefore, the angle POQ equals 2 theta by the angle sum property in a triangle. And we know that by the inscribed angle theorem, angle subtended at the circumference of a segment is nothing but half the angle subtended by it in the center of the circle. So POQ is 2 theta shall imply angle PXQ equals theta. So the proof is quite easier, but learning it how to apply in the problems in suitable conditions is a challenging task. So let's solve a problem based on this. So here is a problem. Suppose in an acute angled triangle ABC, let me draw it, you have a circle passing through A and B and tangent to BC at B. So this circle is named to be gamma B and it would look like this. And when you consider the circle passing through A and C, which is tangent to BC at C, it would look like this. And this point would be named as HA, which is the intersection of gamma B and gamma C. So this is our gamma B and this is our gamma C. And the intersection of these two circles should be named as HA, which is the other point of. Now, proving that the orthocenter of the triangle ABC lying on the circumcircle of BHAC can be done using inscribed angle theorem, and actually not the forward way but the reverse way. That is, if the angle subtended by the line segment BC on the points HA and H are the same, then it turns out that all these 4 points are concyclic. So what I'm trying to prove is that angle BHAC equals angle BHC, because this implies that if you consider the angle subtended by the segment BC at the point HA, say it is some angle alpha, if it is equal to the angle subtended by BC at the point H, then these 4 points are concyclic by the converse of inscribed angle theorem, because they both lie on the same side of the segment BC, because since acute angled triangle has its orthocenter inside the triangle, this is necessarily true. And since both these points H and HA both lie on the same side of, which is in the same side of the actual triangle, then these 4 points would be concyclic. Alright, let's go ahead with finding angle BHA. So let's not find it directly. At first, join the points A and H. Now, notice that BC is tangent to both gamma B and gamma C. So, which means we can apply the tangent chord theorem here, because we have a tangent and the chord to be BA. So, consider the chord as BA. So, this angle would be B. This clearly means that the chord AB would subtend the same angle B on the alternate segment of the circle gamma B. So which means the angle subtended by the chord AB would be B here. Let's take some random point X on the alternate segment. So if that is B, then HA is its opposite vertex in the cyclic quadrilateral XAHAB. So the angle AHAB would be 180 minus B, because opposite angles are supplementary in a cyclic quadrilateral. This also comes from the inscribed angle theorem. And when you consider the other circle gamma C, by a similar argument, one could prove that this is angle 180 minus C, because the chord AC subtends angle C with the tangent. So you can again take some arbitrary point on the circle gamma C, namely Y, the point Y, and considering quadrilateral YAHAC, you will get the angle AHAC as its opposite angle. So this would be C. So opposite angle would be 180 minus C. Now, we know the whole angle is 360 degrees, and hence 180 minus B, 180 minus C adds up to 180 minus B minus C plus 180, which is nothing but 180 plus A. Now, in order to make it 360, this angle needs to be 180 minus, and thus we get the angle measure of BHAC to be 180 minus. So this is a consequence of applying tangent chord theorem or the alternate segment theorem. But analyzing the angle BHC is quite simple. So let's look into this. If you have a triangle, the same triangle ABC, and let us think about its orthocenter H as the intersection of altitudes of this triangle. Let's name the foot of perpendiculars to be D, E, F respectively from the vertices A, B's. Notice this. This angle is C, which means angle CBE would measure 90 minus because BEC is 90. And by a similar logic, angle BCF would be 90 minus B, and that implies angle BHC equals 180 minus A by the angle sum property. So now we get some beautiful result. Isn't this fascinating? Because both BHAC and BHC are equal and we have proved our required result. The points B, C, H, HA are concyclic. Thus, the circumcircle of triangle BHAC passes through the orthocenter of triangle ABC. And here, I did not mention the name of HA. I actually disguised it as some intersection of two random circles, but actually special point in geometry named as the A Humpty point. And there are more properties of this point which I did not mention. You can work on these properties and develop more properties of this. So I hope we have learned something essential today, and you can practice more problems on this alternate segment theorem from problems in INMO, RMO, and AMCs. So this will be quite helpful for preparing towards those exams. So all the best, and we will meet in the next video. Thank you. Bye.